So I wanted to go over a few examples of how to graph piecewise functions. When we have a piecewise function, they give us 2, 3, however many different equations that they want our function to be defined for separate portions of the domain. So here, for example, the function g of x is supposed to equal 1/3 x plus 3 for any x that is less than 3, which means anywhere from negative infinity up to really, really close to 3. This equation is going to define that graph. And then negative x for x being greater than or equal to 3, which means from 3 to positive infinity, this function is going to be defined by this equation, negative x. So when we're graphing them, I generally like to have an idea of what sort of basic shape my graph is supposed to take. I also generally like to really know what's happening at this changeover from one equation definition to the other equation definition, because I want to see if they meet, if they don't, what the jump looks like. So we kind of have to go back to making tables for a bit. So for example, here for this part of the function, x and y, which is really g of x for us, we want to make a table for ourselves. And I want to know what's happening before x gets to 3. So for example, I might plug in something like 0. And I also really want to know what's happening at 3. So I'm going to plug in 3. Even though it's not defined for x being equal to 3, I can still put an open circle there, and I'd like to be able to do that in the accurate spot. So if I'm plugging in 0 to this equation for the function, not this one, only 1, I would have 1/3 times 0 plus 3. 1/3 times 0 is just 0, so now I have 0 plus 3, and 0 plus 3 is just 3. So for this thing, I have in the ordered pair 0, 3. And then I want to do the same thing now with this other value of 3. I know it says less than 3, but again, I just want to know what's happening at 3, so I can put an open dot there. So I'm going to have 1/3 times 3 plus 3. Well, 1/3 times 3 is the same thing as 1/3 times 3/1. That's going to give me, when I multiply 3/3 plus 3, any number over itself is, of course, 1. 1 plus 3 gives me 4. So when I plug in 3, I get an output value of 4. So this is another point I'm going to use on my graph when I create it. Then I'm going to see what's happening for the next portion of the function that says once I hit 3, now my function is supposed to be defined by this equation, negative x. So again, I'd like to know what's happening at this changeover point of 3. So here I used 1/3 x plus 3. And now I'm going to use the other equation they gave me, which is negative x. And I'm going to plug in a value of 3. And this says for x greater than or equal to 3. So I plugged in 3 to know what's happening at the changeover. And then I want to plug in something bigger than 3. I don't care what's happening before 3 for this equation, because before 3 my function is being defined by this equation, which is why here I plugged in something that was less than 3. And then I cared about that changeover point, which is why I plugged in 3. So 3, and let's say I wanted to know what's happening at 5. You can pick anything bigger than 3. I'm just randomly picking these values. So if I plug in 3 into this equation, my equation is negative, and then whatever the value is for x, well, negative times 3 is just negative 3. So I have the point 3, negative 3. Oops, over here I messed up my point. This point was supposed to be 3, 4. And then if I plug in 5, well, negative of the input value 5 is negative 5. So I have another point, another ordered pair of negative 5, 5. So now I have 4 different points to help me graph this. I know that because these are both linear equations, that they're going to either be doing an increase or a decrease depending on the slope. So that's why I don't have to worry too much about curves and turns, because they're linear equations. So, excuse me, I'm going to go over here. I couldn't find my graph paper when I went to go make the video. So we had this point of 0, 3, so 0, 1, 2, 3, we'll put that here. And then at 3, 1, 2, 3, we had a value of 4, which would be up one more. And so normally for a regular graph, we would put this filled circle here and connect those. But again, this is a different kind of function. It's a piecewise function. So this thing tells me that this equation does not work when x is actually equal to 3. But I know that it's supposed to be going in that direction, so I'm going to put an open circle right here. So this just means this is getting really close to a point on my graph, but this actually isn't going to be a point on my graph, so I'll have this open circle. And then for this other line that they gave me to define my equation, my function of negative x, when I plugged in 3 to that, I got an output value of negative 3. And this is actually a point I get to use because the definition tells me when x is greater than or equal to 3, it's defined by this equation. So I'm going to put in a full circle on that point at 3, negative 3. And then I have that other point at 5, negative 5, 4, 5, negative 4, negative 5, which will be about here. And again, that's in the domain that was defined of the equation, so I can go ahead and keep a full circle. So again, like I said, I know these are lines, so these two are one line that's going to be connecting. These other two are another line that will be connecting. And so this is the graph of the piecewise function that they gave me originally. Let's do one more. Sorry. So I have here another piecewise function. This one has 3 different equations defining it, just so we can see something slightly more complicated. Again, I need to know what's happening either before this changeover value of negative 2 and 0, or after that changeover value of 0 or negative 2. So I'm going to again make myself a chart, only here I'm going to be using 3 different equations to figure out what my output values are supposed to be for this function instead of the 2 that they gave me for my definition last time. So this says it's defined by this equation negative x plus 4 whenever x is less than negative 2. So something less than negative 2 would be something like maybe negative 5. And even though it's not defined by this equation at negative 2, I still want to know what it looks like at negative 2 so that I know what that changeover point is going to look like for us. So I'm going to plug in negative 2. And here, remember, we're going to use that negative x plus 4 to figure out what our function looks like. F of x, not g of x. Okay, so we have the opposite of our x value, which is negative 5, plus 4. Well, opposite of negative 5 is positive 5. Plus 4 gives me 9. So I have the ordered pair negative 5, positive 9. Negative 2, I have the opposite of negative 2, plus 4, so 2 plus 4, to give me 6. So another ordered pair of negative 2, 6. Then at negative 2, it jumps to being defined by this equation, which is a constant function. So here this is a linear equation that had a negative slope. I expect it to look something vaguely like this. This is a constant function, which means I expect it to look like a horizontal line. So I'm going to do my next set of things. Now I'm using this equation of 3 to define that function because they told me to do that. I'm going to again plug in that changeover point of negative 2. I could plug in something between negative 2 and 0. There's really not going to be a point in doing that here though, because this function is a constant function. So I could also plug in, say, that changeover value for x of 0. So for this function, there's no input. Doesn't matter what x is. My output will continue to be just plain old 3. So I have these ordered pairs now, negative 2, 3, and 0, 3. So this portion of my graph I expect to look something like this. This one I expect it to look like this. And then I have this quadratic equation, x squared plus 6, for the rest of the domain where x is greater than 0. And again, if we remember what our basic functions look like, we expect that thing to look either like part of this or all of this, depending on how it is defined. And if we remember our basic parabolas, they do have their vertex at 0. We're not shifting this thing left or right. So I do expect that at 0, I'll be at a low point for this particular parabola. So I'm using this equation for now. Our changeover value is again 0, so I'm going to plug in 0. And then it says x has to be greater than 0, so I can plug in anything I feel like as long as it's bigger than 0. So let's say I felt like plugging in 2. If you want to plug in 7, 12, whatever you want to plug in as long as it's bigger than 0. So if I substitute 0 into this function, I would have 0 squared plus 6, which is just 0 plus 6, so 6. So my ordered pair is 0, 6. And then if I plug in 2, 2 squared plus 4, 2 squared plus 6, which gives me 4 plus 6, so 10. So my another ordered pair of 2, 10. So now I have all these ordered pairs, and again I'm going to use this to create my graph, along with my general knowledge about what these functions are supposed to look like. So I'm going to go down here. We had the point negative 5, 9. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. So about here. Negative 2, 6. So negative 2 up 1, 2, 3, 4, 5, 6. So around here. Oops. And this should be an open circle. Sorry, not a closed circle, because remember it was not defined for it at negative 2, it just said less than negative 2. And we said this was supposed to have this basic shape like another linear equation. So this will look like this. We said at the changeover of negative 2, it then jumped to this value of 3 because of the way the function was defined. So at negative 2, I will have this value right here. And that gets to be this value until we hit the value of 0 for x. And so I am going to have a full circle. So it'll look like that right there. And then lastly, it starts to go into that parabolic function. At 0, we did the math and it came out to be 6. So 3, 4, 5, 6. We're back up here. This is going to be an open circle again. And then at 2, we had a value of 10. 1, 2, 3, 4, 5, 6, 7, 8, 10. So about here. And it'll look like this. So these are two examples of piecewise functions. When we graph them, what we should never see happening is that these graphs are sitting on top of each other or overlapping with each other, because then we don't really have a function. I hope that helps. Please keep sending your questions.